Hello everyone. Here I'm with another video about using neural networks and deep learning in MATLAB to estimate body pose. Basically, how different limbs of a person are situated, are oriented, where they are, and how they are oriented in an image. So we can see if the person is standing, running, sitting, and so on. This is done with the neural network called OpenPose, which is an open source network developed by researchers at Carnegie Mellon. It's really state of the art, does a fantastic job, and it can handle several people. Now, it doesn't mean it's perfect. Nothing is perfect. When there are occlusions and too many people, it might have some shortcomings as well. But I tried it here, and you'll see I tried it on basically this image here, 4 people playing soccer, and each one of them clearly in different body pose, and it did a really fantastic job. So I want to tell you that some of the pictures here that I use for explanations, like this one, and these, they are coming from this website, medium.com, and they have done a fantastic job explaining this topic. So I'm borrowing their pictures, and the copyright really of these pictures belong to these people. I don't claim anything. And this network that is pre-trained can be downloaded from MathWork website, the zip folder that contains the weights, biases, everything for this network can be downloaded from this address. Okay, so you go there and download the zip folder and put it in the same folder that all of these files for this body pose estimation are. Here is your main file, but it needs a lot of helper files. When I give you download link, I'm gonna basically put all of it in a zipped folder, all of it, including this pre-trained network. And I want to tell you that all of these helper functions are written by MathWork, okay? None of them are written by me, and I'm here using the commands in MATLAB to explain the topic, okay? So I do not claim any authorship. Now, this network has 2 parallel branches and 6 stages. So it's multi-stage and parallel multi-branch. Amazing, huh? What does it do? Well, the whole thing, as you can imagine, is a convolution neural network. As you can see, the top branch, the bottom branch, they are all convolution. What you pass to it in the first stage for both top and bottom branch are the features of the image. This F here are the image features, and C means convolution. So you see here that like the first stage has 5 convolutions, right? And a fully connected network with a specific loss function, a different loss function for the top one and the bottom one, right? And you see, but they have both 5 layers of convolution. If you go to stage 2, now you're going to see there are 7 of them, right? And there are different stages, and I'll explain why. So what are the outputs of these layers? The top branch layers, they create what we call a heat map, okay? And heat maps are basically like the probabilities that each key point in the body, for instance, a wrist point, a nose, a shoulder point, an elbow point, a knee point, those points, whether those points exist in an image, if they are, where are they in the image, and with what probability. So they create heat maps or confidential confidence maps, I'm sorry. Now, the bottom layers create something we call PAF, or part affinity fields. These are 2D vector fields, X and Y, and they contain basically a vector field that shows how each one of these key points are connected together to form a limb. Okay, let me tell you what I mean here. So in this method, they kind of depicted the body as something like this. They considered 19 key points from 0 to 17 plus an extra one, which is for the background. Okay, so there are going to be, and you see index here in that system that they wrote, index started from 0. In MATLAB, it starts from 1. But if you look here, there are 18 key points plus 1 for background, which is the 19th key point. which is the whole background, and each one of them correspond to something. For instance, key point 0 corresponds to nose of a person. Okay. Now, clearly each limb is formed by connecting these key points together, right? So, for instance, you can say that from, let's say, 8 to 9 is probably could be a leg, or 9 to 10 is the shank, right? Or 3 to 4 is like forearm, right forearm, and 6 to 7 is the left forearm. Of course, here we are talking about the person in the image, not the way that we see, because if you see a person like this side is the right side, this side is their left side. Okay, so this is a heat map. This is how a heat map would look like. So here, what you can see for this guy is a left shoulder key point, which is key point 5, and that is for this lady that they are doing this dancing together, right? So you see that the center of it, that is the highest probability, that's exactly the center of the shoulder, is red, and as you get away from the shoulder, they fade very fast, and they kind of form something like a Gaussian distribution or so. They are not perfectly Gaussian, as you can see, but this is basically a distribution. This is a probability distribution around a center point, and that detects a key point. This is the output of the top branch, and the bottom branch, as I said, is a vector field, a 2D vector field, which we call part affinity field, or PAF, which is basically something like this. So this time you're looking at what? You're looking at a limb instead of a key point. Okay, and then if you detect the presence of a limb, you also show the vector field for how it is connected. For instance, if this point here is the left shoulder and this point here is the left elbow, the way that the arm is basically oriented is from the shoulder to the elbow. So it is from this point here to this point down there. So this vector field, right? This is kind of like an optical flow field. This is basically the direction from the shoulder to the elbow. Okay, for one limb that was detected as being present in this image, or a similar thing, a similar vector field can be there. And there are 38 channels for the paths, 2 channels for each body limb, because it has the X field and the Y field for that vector field. Okay, so there are 38 channels of that, 19 channels for the key points. So as I said, this is the output of this top 3 pictures are the outputs of the top branch. These guys are the outputs of the bottom branch, key points and the limbs. Now, why do you have multiple stages? So because as you go from one stage to the next, the output from the first stage is passed as the input of the second stage. So the input to the second stage are not the image features anymore. They are what? They are these confidence maps or heat maps and these fabs, right? Paths, sorry. These paths from what? From the basically first layer. And if you want, you can also add what? You can also add the image features as well. So you see here, these image features are also passed to what? To the top and the bottom branch of the second stage, and so on and so forth. So you can still pass these features to all of the stages, but you also pass the outputs of the previous layers. Why would you do that? Because by adding more stages, the false positives will be eliminated over as you move on through the stages. So here, for instance, you can see there are 5 spots, right, that are detected for the right hand wrist. And this is in stage 1. Now, as you went to stage 3, you can see that this point here, which is clearly, as you can see, that's not the wrist of anybody. Okay, you can see that probably better here, that that's not basically a left wrist, that's a right wrist. that one is eliminated as you move on, and here is completely gone. And this one as well, okay? This one, which was also a right wrist, was eliminated. So only these three left wrists, this one, and even that one is, you can see that here, this one is also gone, right? Because that one is a what? Is the left wrist of this person, while it might look like, no, that's the right of this guy, but it's not. It's the left of this one. The right wrist of this one is correctly detected, and the right of this one. The right of this guy is behind that person, is occluded. You cannot see it. And here are what? The right arms. As you can see, there are some false positives here. And as you move on, this false positive here is eliminated, okay? So, because you cannot see that all, it's occluded. And so this portion stays for this right arm, that right arm stays, and this right arm stays. Now here, there is a false positive. If you look, this is kind of like a bag or something, a band of a backpack or something that is detected like a right hand. So it's not going to be perfect, but as you move on and you use more stages, hopefully you get better results. So now that you detect these two outputs from the very last stage, and as I said, there are 6 stages in the OpenPose network, then what would you do? Now, of course, one of the things that is important in the creation of this bottom layer is not all key points are supposed to be connected together, right? You're not going to connect the nose to the foot or nose to the wrist or anything. So there should be some connection that is only valid for a specific key point to another specific key point to form a limb. So here you should have some pairs, and these pairs correspond to what? To the physical limbs. Okay, so as you can see, 0 can only be connected to 1, for instance, right? But you don't see a 0 to 10 or 13 anywhere in this specific pairs that are allowed. Good. So now what? Now, if you want to use this, the first thing you do is, as I said, you download the zip folder, which you did. You put it in the current location, the current folder that you have. And then what? Then you use the unzip command. You pass to it the current folder, which I got using the cd command, current directory. You pass to it the name of that zip folder, and it creates the unzipped version of it. Then here you start what? Extracting the network out of the zip folder using the full file command and the network file, which is ONNX type of file. And of course, you import the weights of this network. Now, this network, it can have some output names layer that you don't need, so you remove those layers. Okay, so this network will give you some names of the limbs and the key points that exist in the image. We don't care about that. We just want to detect them so we can overlay the limbs on the image, like this last one that you can see, right? So you see here, for instance, these green members, these green lines are like the right side of the body. These kind of cyan and blue ones are the left side. The yellow is the left hand. The red is kind of the right hand. This blue one is like the neck, correct? And so on and so forth, right? And so you want to overlay this, and you don't want to name anything. So any layer that makes the system slow, you're going to get rid of it, and that's what you did. And here you convert them to deep learning network. Okay, DL means deep learning. So you convert those layers to the deep learning networks that are usable in MATLAB. Now what? Now you load your image. Here is the image that I got from the internet. I show it first. Then this image directly cannot be passed to that network. You have to pre-process it. Why? because that image, first of all, the type of the image that you can pass to that network, the type of the data should be single, not double, not uint8. So you convert image to single, and the single data are between 0 and 1, but that network expect the data to be between negative 0.5 to 0.5. They are normalized, centered around 0. So you subtract the 0.1, 0.5 from everything. So the net input is between negative 0.5 to 0.5, as I said, centered around 0. And then the other thing is you have to shuffle the, not shuffle really, basically change the order of the color channels. Why? Because the way that this network expect the channels, the color channels of the image, is blue, green, red, not red, green, blue, as it's not RGB, it's BGR, which is common in OpenCV. So here you see that you're changing the channels. Instead of 1, 2, 3, you do 3, 2, 1. Okay? And then you save that input as a deep learning array. DL array means what? Means deep learning array. Now your input is ready, is pre-processed, your network is ready, and so now it is time to give this image to the network that is already trained. You don't need to train it and do anything about it. So now you use the command predict. Pass the network to it, pass the image to it, and it returns two things, as I said, the heat maps, the outputs of the very last stage top branch, and the paths, the output of the bottom branch of the last stage. Okay? Now that you get the heat maps, you can extract them to get the heat maps that you can show. And you get rid of what? You get rid of the last heat map, which is the background heat map. Remember, one of the last key point or the last heat map is background, so you get rid of it. Now here to show you the result, for index number 1, which is the nose, if you remember, the key point 0, ID 0, I have overlaid the heat maps for the nose on the top of the original image, okay? So you see that these are the heat maps. They have been resized to the size of the image, and I use the IMShow pair to overlay these heat maps onto the image, and this is the result, as you can see. You can see that for these 3 people, the nose is correctly detected, and this person whose face is the other way, you don't see a nose. Okay, so it is correctly detecting the noses in the image. Also, you extract the paths, and here again, I show you what? I show you from index 0 to index 1. Of course, actually, no, that's 1, so it's going to be from index 1 to index 2, which is connecting 2 key points to form a limb, and in this case the limb is basically like a right side backbone. Okay, basically it's this guy. If I go back, it's this guy from 1 to 8. It's this one. By the way, if you looked at the model of this pose estimation, it does not consider one limb for the trunk of the person and then connecting the end of that one limb to what? To the top of the right leg and the top of the left leg, the hip bones, basically. So the way that here the trunk is modeled is really by this triangle 1, 8, and 11, although 8 and 11 are not connected. If it did connect 8 to 11, it made it look a lot nicer than the way it is. This is kind of a little bit weird, but that's how this model, which is called, I guess it's called COCO data, right? This is the model that's trained on the COCO data. You see here it says COCO pairs. This is how it was considered. And you can change it if you change these helper functions, which I'll talk about later. So now you can see that these are what? These are on the two sides. These are what? These are the right side of the trunk, as you can see. These are those limbs. These are those vector fields, right? You see their magnitudes here, and if you want, you can show their X and Y component. Now, if you look here, you're only showing basically one component of it on the right side and one component of it on the what? On the left side, like X and Y. Okay, and if you want, you can visualize it with a vector field like this as well, but here basically the X and Y components are plotted separately instead of a magnitude like that. As I said, you can use the quiver plot and basically show the vector field. So these are those detected limbs. These are the detected key points with the direction of the limbs, of course. Now that you have all of these individual components detected, individual limbs and key points detected, you have to connect them together properly. So if you detect, for instance, what? A right hip bone or something here, or I don't know, let's say a right shoulder for this person and the bottom of the neck, you have to connect those two for this person and not the shoulder of this person to basically the neck of this one. So you have to connect the ones that belong to the same person, not to different people. Okay? Because you have detected a bunch of limbs and a bunch of key points, but you don't know which one belongs to whom. So this is that post-processing that you need to do. The first thing you do here, you have this helper function called getBodyPoseParameters. It returns these parameters and the constant that the next helper function called getBodyPoses does need. Now, how does this guy look like? If you look at this, here basically tells you which pairs you're allowed to have. For instance, the neck can be connected to the left shoulder. The neck can be connected to what? The right shoulder. So basically, that's this pair thing that I showed you here. It is defining that, right? And then the indices for them return as a matrix. Okay, and once it defines all of those and which kind of colors, right? The minimum number of parts to be considered for a valid pose. You see, so if you don't have more or less more than or equal to 5 parts in a body, you're not going to connect them together and you're not going to call it a valid pose, right? And there are affinity, score, and a bunch of constants. So all this function does define the constants and the parameters. Now what? Now you pass those constants and parameters that are important along with the heat maps and those paths to this main function getBodyPoses, and it returns what? The poses, and that is this guy here. And the output of it is a matrix. Okay? Right? The output of it is, the input of it is a matrix of heat maps, paths, and parameters. The output of it is a matrix, as I said, of what? The locations of each body part for each person in the image. Okay, if the body part is not found, then you turn a nan. So here, now that you have the locations of these body parts, now you use this last helper function, which takes all those poses, the original image, and the sizes of the heat maps and the parameters, and this guy will what? Will plot, basically will connect and will plot what? These lines that you can see, which represent basically this skeleton picture, okay, or this pose, what you might call. So here is called render body pose helper function, which is this guy, and you see that basically this one, if you look at it, it just does a plot for you, right? You see there is an I am show, and it converts these coordinates, right, to some numbers that you can basically do a line. And here you see that each time the color is changing, and it creates a color for each limb different. It uses a different color for each limb, basically. So the main optimization part, the main part that connects those different detected key points and limbs together, is this guy, getBodyPose. that is where the main optimization and the search, we call it the greedy search, is done here. And this is the one that picks the candidates, okay, and the scores. So what is that? Let me try to explain that briefly. So maybe this picture is good. Yeah. So look here. I have these two blue points here, let's say in this picture, detected as the elbows, the left elbow, and these two green points as the left shoulder. So now, what are the scenarios? I can connect this left shoulder to this left elbow, or this left shoulder to that left elbow, and the similar thing for this other one. So there are 4 connections or 4 limbs here. Now, which one of these 4 limbs would you keep? Which one of them would you throw away? That's where you have to compare these arrows connecting the shoulders to the elbows against what? Against those paths that you got from what? That you got from this bottom branch. So the bottom branch says, hey, I should have a limb with this direction in this location, correct? So when you go down, you see here those paths are overlaid. Well, of course, this arrow here between that green point and that blue point, that is better match for that path than what? Than this guy here. So clearly this is going to get a low score. That one is going to get a high score, because the arrow connecting the green point to the blue point here matches one of those paths. And a similar thing here, this one connecting to that creates this arrow which matches this path here. There is no path in this direction in this image. So that guy gets a low score, that one gets a high score. So we're going to keep those two, and we're going to get rid of these 2 long ones. So that is basically what you do. And this first part, that you first form all of these different arrows, all of the possible ones, the result of this is what we call a bipartite graph. And then you basically prune and get rid of the edges that in that graph that will have a small weight, and only keep the strong ones by comparing against the paths. And so your final graph is going to be a bunch of separated individual graphs where each one is what? The pose for each person. And this is the result. If you want to see that, right, you can very well see that. Look here, this knee that is bent, this one that is straight, these hands that are bent, perfectly shown. The head is not shown. Why? Because this guy, we could not detect the nose for it. But for this one, you see the direction of the neck. Look how the hands are bent. Look at the leg. Look, this one is like this. This one is like... Now, look at this one. This is interesting. Here, you see a mistake. Look, this green part, if you look at it, the computer thinks that this shank belongs to the right side. And for the left one, it does not detect anything. Well, clearly, because here, this leg basically occludes the other one, this is clearly making the algorithm have an error. But here you see it is doing it fine because there is no overlap and occlusion like that. And here again, it is doing relatively fine. Okay. So also one other thing is the eye or the head also has 2 branches here. Okay, so you can have the head this way or facing that way. And that is another thing. So one goes from the nose to the right eye, one goes from the nose to the left eye. And you can probably see that over here as well, because this guy, both of the eyes are clear. And this one seems like this branch was not detected properly. That's interesting. And this one, of course, you cannot detect anything. Okay, and the eye was closed. Probably the eye was not detected brilliantly. Okay, because the branch for the eye should be red, as you can see here. So it's not going to be perfect. Nothing is going to be perfect, but understanding the difficulty of this task for this pose estimation of these people, all different conditions, it is doing an amazing job. So as I said, I'm gonna give you a download link for all of the files that I'm using. All of them are written by MATLAB. The only one that I modified is this live script here. This is the only one that I created and modified, basically based on these pre-existing functions. And hopefully this video is useful to you. Thank you so much for your attention. I'll see you next time.